proportions. So think about this when we use these equations right here and cross multiply that you all love to do. What's another word that we can use for this? I mean, we call it a proportionality. But think about another word that we would use. And I'll help you. So we have these two. What do we have here?
Pepsi and Pepsi.
Right.
Pepsi Cola.
What's different about those? Well, maybe I should have bought them all the same material. That is true. But thinking more of like volume. One's bigger, right? This one's 12 ounces, and this one's 20 ounces.
I'm skinny.
So, it's a cute bottle. I like it. So let's see. Let's look at it, and it has total carbs are 40 grams in here. All right. That's what the bottle says, right? So we have 40 grams in here. So, does that mean that there's 40 grams of carbs in here? No. Why?
Carb is proportional to the volume.
Because it's proportional. And what's another word? Maybe a smaller word that you might be more familiar with that would explain if you took a taste of this one, would it taste the same as this one?
It would taste the same.
It would taste the same. So what's that say about the ingredients to the water?
Pepsi makes them
Proportional.
proportional.
They do. And what's another word that we're familiar with that might be easier to remember? It starts with an R. Think of your water, and then you add, some Kool-Aid or lemonade, things in there. There's a
Ratio.
ratio. So isn't ratio, when we say that this is a ratio, right? That proportionality? Ratio might make more sense to you. It's just something you're more familiar with, and you can see that our ratio is the same, because they're all going to taste the same, right? But if we have, say, 40 carbs here, that doesn't mean 40 carbs there, but yet they all taste the same. So that ratio has to, so there must be a constant, right? That ratio, that factor that is the same throughout, so that we can make a small amount or a large amount and have it still taste the same. And again, that's another concept that we're all very familiar with. It's just putting it into that context of calling it a proportion or a proportionality. And what does that constant mean? So, in talking about these sale prices and these original costs, could we graphically represent this?
Yes.
What would that graph look like?
Straight
What do
line.
you think, Zach? It would be a linear, right? Would it go through 0, 0? Could we say that if it's 0 original cost, the sale price is going to be 0? So we set up like this. There is our original cost, and we have our sale price. And we can stick them on a graph, just like we've been doing, whether it's pressure, temperature, volume, temperature, right? Your original cost on the x-axis, your sale price is up there on the y. And you have all your little points. You've drawn this line, right? Your line of best fit. But what's the equation? Do you see that equation on there? Where did this value come from?
That's the constant.
That's that constant, right? That was that discount that was the sales at the whole store. And what that's saying is that no matter what price, you could go way out here if it was $1,000, $2,559, whatever that original cost was, we can determine what that sale price is. Right? And then we do that all the time. So on your elaborate 4, number 75 in your packets, let's take a look at that one.
Just look at it.
Wow. Some of us did not like this question at all, did not understand why it was asked what it was or where it was heading with it. So there's kind of two parts to it. One, it's just telling us a mathematical law. It's just telling us about something that has been proven in algebra. And that is that if one variable is proportional to two different variables, then it's proportional to the product of those two. I know that's a lot of words and it sounds really confusing. So what it's saying is that if x is proportional to y, and x is also proportional to z, then it's the same thing to say that x is proportional to y times z. But I wasn't asking you to do anything with that specifically, it was just telling you that, hey, this is an algebra fact. Some of us really wanted to see that. We're either in math classes now, or you've taken them before, and you're like, I don't know, this wasn't making sense to you. So, I am proposing to you, consider this a bonus question. You research this. If you're in a math class now, talk to your math teacher, look in your math book, look online, library, whether it's here, public library, they have textbooks, they have math books. See if you can't find the proof. Because for every law and math, all these algebra rules that we use, there's always the proofs where it'll show you this and go step by step with an example and show how, hey, this is true. So you find the law and give me the detailed breakdown on that, the proof, we call them the proofs of this law, and that'll be worth bonus points for you, just extra credit in here, okay? But for now, for these purposes, we're going to accept that, okay, they're telling us that this is true. This is an algebra fact. So if this is our algebra facts, we're going to use this concept along with Boyle's law and our Hamilton's law that we've just studied to find that relationship between all three variables of volume, temperature, and pressure. So what is Boyle's law? Andrew, what's Boyle's law? So pressure is proportional